Hello everyone and welcome to this fourth lecture on the course Digital Image Processing of Remote Sensing Data. In this lecture we will be mainly discussing the image characteristics and different resolutions in remote sensing. Very briefly these things we have already discussed, but in this particular topic I will be going in much detail. This slide you have already seen in very first lecture. A picture tells 1000 words and a satellite image tells 10,000 words. So after going this the third lecture, that is digital image processing, the introduction, now you might have realized that yes, a satellite image can tell 1000 words after the processing, analysis and interpretations and inferences. So a lot of inferences can be made. So that is why I am repeating this this particular slide and few more slides, because now we know that what we are going to do in digital image processing. In very brief I have discussed in previous lecture, but in later lectures we will be discussing. So picture tells 1000 words and satellite image can tell 10,000 words, which we will be realizing one after another throughout this course. And because digital image processing, through digital image processing we can improve the images to a very large extent, and this is happening. Also we have there are two things which I want to re-emphasize here. One has to understand what is basically an image, and second is the unit of an image. In brief we have discussed these things in very first lecture, that image is a pictorial representation, but it is fine. Now let's concentrate mainly on the image which is being acquired by a satellite sensor or a sensor on board of a satellite. So we are now not discuss any other source of image except the satellite based. So you know that there are various types of scanning processes or non-scanning processes, or various acquisition systems are there. And that is why in this particular lecture many slides will be repeated, but because it was very much required, so that in between the lectures which we have covered now, we can go and focus mainly on the satellite based digital image processing, because digital image processing are in different fields. In electronics, digital image processing meaning altogether different. In medical science, digital image processing is altogether different, whereas in this remote sensing and digital image processing of remote sensing data is different, though fundamentally or from the background in the mathematics which is in the background might be same, but the purposes are different, and therefore the sequence of image processing and the handling and different steps are altogether different. Like in maybe in image classification may not be required in electronics or in medical imaging, but image classification is very much required in remote sensing applications. So that is why we would like to discuss this thing. So once a satellite has acquired an image of any resolution, let's take example of 80 meter resolution from Landsat MSS, and when it has acquired by the sensor, transmitted by the satellite, has reached to a system, then you must understand that image is a two-dimensional matrix, and each cell of this matrix, which we call as pixel, will have one pixel value, and depending on the radiometric resolution these pixel values will vary. And also these pixel values will vary because they depends on the, if we are talking about the visible channel data, then they will depend on the reflectivity of the objects in the solar lights or solar illumination. So and the unit of an image, which is a pixel. So these things have to be remembered, and again I am repeating that this will make things very clear that the overall shape of an image can be either rectangular or square, but the unit is always a square. That means pixel will represent a square part of the land. And let me show you one example here, that if you see a raw satellite image, what you would find that it is having something like this kind of appearance. Now you might say that you told me that an image, overall shape of an image either can be rectangular or square, but this image is appearing not exactly a square or rectangular. But in computers, the image will always be, as I have mentioned, the image will always be stored either rectangular or square. So rest of the areas, these areas will have the no data. No data is also a data, but it is the data which is not, that kind of pixel value will not exist within that image. So the system or the program, the image processing program can identify this thing very easily. So that is why an image on your screen, a raw image on your screen might appear like this, but actually the image in the computer is stored in a rectangular or square fashion. So this one should make very clear. The same scenario I can take, an image might be appearing like this, but if you see very carefully, you will find that image has been stored as a square. So this area will go as no data. And no data is a very good concept to represent the areas where basically the pixel values are there, but they are very different than what within the images are. So no data values can be declared to the system, that if the system encounters any pixel value, say for example -999, then consider as a no data and do not include in image processing. So this is how, that is why we see different, because the screen generally is having the black background, and if we assign to no data values the 0 or the black value, then we don't see this area, the triangular, this area, we only see the image part. So but overall shape of an image can only be square or rectangular. This is very important to understand. And second is that the unit of an image will always be square. So this will always be squared in the, if I enlarge it, this is always square. Now when we say spatial resolution, say if I took the example of Landsat MSS, say 80 meter resolution, we only mention only the one side of this. We do not mention that 80 meter by 80 meter. We say 80 meter. If it is a 10 meter by 10 meter, we say 10 meter resolution. But what it is representing basically, say in this example, 10 meter by 10 meter, it is representing 100 square meter area. But in saying, we say 10 meter resolution. So because we assumed or have understood that the shape of a unit, that is pixel, will always is square. So only one value while telling about the spatial resolution is very much sufficient. We have also discussed the different images, analog and digital. Now we will talk only the digital images. No, we will not talk the analog images. And digital images, we have seen now, we have discussed different types of sensors. So maybe electro-optical sensors, or maybe just simple CCDs, an array of CCDs which we have seen through in some scanners, along track, across track scanners, they acquire the data. There are now a lot of innovations are happening in scanning systems as well, especially which are going on board of different satellites, so that the better quality digital image with the minimum signal to noise ratio or can be acquired, so that the processing is reduced and things can be. This I have already discussed, and which I have already said. Now in what we find in different literature or different discussions, people call different things, different numbers. Somebody would like to pixel value, they call as digital number. Somebody like to mention a brightness value. So depending on the type of image or the band of which it is representing the EM part or electromagnetic part of a spectrum. So if I am talking say for example a thermal image, then the pixel value becomes my brightness temperature. But if I am talking a visual image, or image belongs to the visual part of EM spectrum, then I am talking about the reflectivity. So brightness value can be there, or overall people say is a digital number, or a very common address to this can be pixel value. Some people use gray levels, but gray levels restrict us only for black and white images. But when we go for color, then this term gray level cannot be used. So therefore one has to be careful while mentioning this thing. Same with our pixel. Because if we look from a computer concept point of view, a raster will have a cell value, and in image we call the unit of a raster is a cell, whereas in case of image the unit of an image is a pixel. So once we say pixel, that means I am talking about an image, not a simple raster, where it is whenever we say raster or we say cell value, that means I am talking about a grid or some other type of raster, not a satellite image. So pixel always is associated with an image where pixel value will be always positive integer value. This one has to remember, the pixel value or digital number or brightness value or brightness temperature or gray level, any name you give, but the value it will have always positive integer value. So these are the minute details one has to remember to better understand the different steps in digital image processing. I have been mentioning digital image, so this is raster, because raster can have two types of raster basically. One raster which we are having is raster we can have two types. So one is image, which we are discussing, a digital image of course, and then another one is the grid. So in case of image, the unit is pixel, but in case of grid we call as cell. Here the values, the cell values, the pixel values, only positive integers. Whereas in case of a grid, that means the cell values of a grid we can have positive and negative integers as well as positive and negative real value. So that means the range which is provided by the grid overall raster is much bigger there but here. But it is deliberate, because an image cannot have a negative value, and it becomes much easier to process such data. Whereas if we want to have a grid, and though it is raster and we want to process, then lot of caring is required in the digital image processing program. So this is another important thing which one has to remember, is that grid can have, and the best example of the most common data which we use in remote sensing or in GIS domain is digital elevation model. Because in digital elevation model, if the digital elevation model belongs to a coastal area where the cell values can have even minus values, because they may be below sea level, and there will be values in coastal areas which are positive values. And if we restrict only to integer values, then you are having problem in case of a digital elevation model, or in case of grid. That means I cannot go for higher precision, and that means I cannot have a elevation value of 1.5 meters or 100.25 meters. So but we know that our pixel values can have only positive integers, so no decimal or no precision is required in this case. But in case of grid, the precision is required. So therefore entire storage, processing, everything is different in case of grid as compared to image. But remember, both are raster. So that is why it is important to discuss here. It is a two-dimensional matrix. This slide again has appeared in the first lecture, but I am taking again because now it's a different kind of discussion. Maybe the topics or the lines which are appearing is the same. It's a two-dimensional matrix. Remember, this is a matrix is a branch of mathematics or part of mathematics. Now, this two-dimensional matrix, so whatever the processing techniques which exist in mathematical domain, it is very easy to import in digital image processing. And that is why, and if we are handling only a positive integer values in case of our satellite images, it becomes little easier rather than the grid values. So two-dimensional handling of two-dimensional matrix is relatively nowadays easier through softwares, and therefore it is employed here. Now we have already discussed this thing that the unit here is pixel and always in square in shape. Overall, we have also discussed that can be square or rectangular. This slide is again appearing as because one has to remember that the pixel values are so, though here for demonstration they are shown here, but basically when you display an image, neither the pixel values are shown, they are on inside the computer, only the pixels are shown, and these are shown in two-dimensional matrix. If you are having a panchromatic image, and then only they will appear in the black and white. If it is 8-bit, the maximum shades of gray you can have an image is are 256. That means the values can vary between 0 to 255 and rest will fall in between, and no lines will appear. No lines will appear, just simple image as you can see here. But just for demonstration and better understanding, these lines or these grid, line grid have been overlaid to understand things. Of course, the values are not displayed, but values are the backbone. So they basically through a concept of LUT, lookup table, these values are converted to shades of gray or colors. So the concept LUT, which we will discuss a little later. And this digital numbers will or the pixel values or shades or colors will come according to what is the radiometric resolution of an image. If it is 8-bit image, then as mentioning here that you might have the shade, one shade out of that palette of 256 colors or shades. In case of a 24 bits image, we can have very large number of colors, and that comes from about 65,000 and 530 this we can have for 8-bit 256, for 24 bits 1.6 million colors. And our standard false color composite images which we prepare using 3 bands out of a multispectral data sets carries a large palette. That doesn't mean that a single image will always have all these colors present within the one single image, not at all. The palette is available, and this palette through lookup table, depending on the pixel values, will be picked up different colors and are displayed on your screen. So this is another important thing, is that depending on the bit size or the radiometric resolution, this is done. As you know that this radiometric resolution is improving at a quite nicely or very high rate as a spatial resolution of remote sensing data. But there are constraints with other resolutions which we will be discussing a little later. So this is, the palette is available, depending on the image, the objects which are present, reflectivity or emissivity, any color for a particular pixel can be picked up out of this palette. So it is not necessary, I am repeating, it is not necessary that each image in a 24-bit image, it will have 1.6 million colors, not at all. The palette is available, it will pick up as per depending on the pixel values. And this is the example earlier also we have discussed, that 1-bit image is just having black and white, 2 extreme members, nothing in between. Whereas in 2 you are having something in between, 4 few more have been added, and a standard 8-bit you are having a palette available of 256 shades here, and image quality has improved tremendously. This 8-bit is more or less standard in various digital image processing softwares as well as with your satellite data. One other important thing I want to bring here in your discussion, that when we started getting from IRS, the IRS 1C 1D panchromatic data, which was in 6 bits. If you recall this one, then we had only 6-bit data. But our digital image processing have been designed to handle of 8 bits data. So it is very easy to always scale up or scale down. Like here in this example, the scale down has been happened. But remember, if I am having just 1-bit image, I cannot convert that image. Though on computers I may store as a 8-bits image, but the quality will not be improved. So from higher bits I can always go for lower bits, but from lower bits image I can never go to higher bits image. So this one has to remember. But in digital image processing, when they handle the images in 8 bits, so the same 6-bit image is handled as a 8-bit image, but the image quality is not improved. But in case of image quality can be deteriorated much easier, but image quality cannot be improved. And same discussion we can also have related with spatial resolution. What I am trying to say is that suppose I am having an image which is representing a 1 kilometer resolution, NOAA VHRR, the best example, 1.1 kilometer. That means the 1100 meters. One pixel is representing 1100 meters by 1100 meters of the area of the ground or surface of the earth. Now using this data and using any types of digital image processing techniques, either based on artificial intelligence or neural network or fuzzy logic, I cannot improve the spatial resolution. That means just taking a roughly 1 kilometer resolution data, that is 1000 meter resolution data, and I cannot convert or bring that image at 1 meter resolution. However, reverse is possible. So resolutions, once the image has been acquired, any kind of resolution cannot be improved. Though deterioration can be done as per our requirements or the handling which is done by the image processing system, but improvements on spatial resolution, on radiometric resolution, on temporal resolutions or spectral resolution cannot be done at all. So this is just one-way process. That is why this image is being repeated again in our discussion, and saying that this was the original image was used to create these images. That doesn't mean that the first one, this image was used to create this 8-bit image. No, this way left to right we cannot go, but right to left we can always go. So we can deteriorate the quality of an image, but we cannot improve quality of an image in terms of bits or in terms of spatial resolution once the image has been acquired by the satellite. So this thing has to be remembered very carefully, because otherwise people claim that they have improved the spatial resolution. No, once an image has been acquired by a device, then spatial resolution by no means can be improved. Otherwise there would not have been any need of launching many satellites, and just 1 kilometer spatial resolution data which is coming from NOAA VHRR can be used to create a 100 meter spatial resolution data, 1 meter or even 10 centimeter spatial resolution data. Not possible. So only say one way, that you can deteriorate the quality, you can do the subsampling, but you cannot improve the quality. Now I am coming back to this color composite for here that to make further clear on this 24-bit concept, because basically it adds because one single image is 8-bit. So when you one single image is 8-bit, and say I assign a blue color to this one, as in the slide is also shown. Another band which is also in 8 bits, I assign green color to this. And then the third one, I am having 8 bits again, and this channel might be my infrared channel, where the vegetation is having a healthy vegetation, might have very good reflection, and I assign the red color. Now if I add this becomes 24 bits. One can argue why you are adding, why don't you multiply? Because remember, these three colors which are shown here, these three discs are shown just for our better understanding. The word is additive color synthesis. This is very, very important for creating color images or color composites, because here we are adding 8-bit plus 8-bit, 8-bit and plus 8-bit, that becomes 24 bits. We don't go for multiplication. So remember, this is because we are following a additive color scheme. Now one can say there can be a subtractive color scheme. Yes, subtractive color scheme also exists, but for display devices, subtractive color scheme is not used. Always the three primary colors and additive color scheme is used. For subtractive color scheme is used for printing devices. And for example, if you are having a color laser printer or even inkjet color printer, you might notice that there are 4 cartridges: one cyan, magenta, yellow and black. So that means the 3 secondary colors are important: cyan, magenta, yellow. The 4th one, black, is kept so that if you subtract these colors from each other, then you will end up with black. So why to waste these 3 colors if a black line or black things have to be printed? So then directly black color will be used. So 2 different schemes, color schemes are used. Additive color schemes are used for display purposes, and subtractive color schemes are used for your printing devices. You might notice in newspapers at the bottom, very bottom, in the either bottom left corner or right corner, you will notice 4 dots in 4 different colors: cyan, magenta, yellow and black. Why they print? So that anybody can check the quality of printing. If all 4 colors are appearing properly, then automatically it means that the quality of printing is quite good. If any one color is missing, then you will not see a proper colored image. So therefore printing you use subtractive color scheme. Here we use the additive color scheme. That is why we add this 8 plus 8 plus 8. Otherwise one can think that why not multiply or subtract on that. Subtraction color scheme is different, and it is used for different purposes. But in the digital image processing, except for printing, in this case we always use additive color scheme. So that is why there is a repetition of this slide. Now because we are going for higher and higher spectral resolution, and therefore number of channels are increasing. However, at the same time, the width of the channel is reducing, and this is very important, so that we are having more choices to pick the bands while making a color composite. And which one to pick might be it requires better understanding about the spectral curves of different objects for which we are targeting. If I am focusing on vegetation part, then I have to remember the spectral curve of vegetation, and accordingly I will choose a channel. The example here, the 7 bands, they are shown for Landsat TM sensors. There are 7 channels are there. That means the same area is being scanned or is being scanned using different parts or different bands of EM spectrum, and therefore that objects in different parts of EM spectrum might appear differently. So only the 4 are shown here, not all 7 are shown here, but the first 3 you might not notice much difference because they are belonging to more or less a visible part of EM spectrum. And a panchromatic sensor may combine all 3, so it is a broad band sensor, whereas in multispectral you may have 3 or 4 bands within your visible part of EM spectrum. The example is given here, that 0.45 to 52 and 0.52 to 59, 0.60 to 68. Another important thing is, it is not necessary that the width of each band within a sensor has to be same. Depending of which part of EM spectrum is being covered, the width will vary. It depends on the sensitivity. Remember, this depends on the sensitivity. In thermal part, the sensitivity is less. That means the energy which is reaching to the sensor is not sufficient enough, and therefore we need to have a broad band so that it can be detected by the sensors. So depending where the sensitivity is high, where is less, and accordingly bandwidth have been designed. Now in earlier cases, and I am giving example of Landsat MSS where the bands were 0.45 to 0.55. So that means there were only difference of 0.1 micrometer was there, but here as you can see it is not like this. So people learned through through the first launch of this civilian satellite, operational satellite, that is Landsat MSS, that the bandwidth should not be equal, and next band was 0.55 to 0.65 and so on and so forth. So the bandwidth were kept equal. Natural objects do not behave in such a systematic manner, and therefore later on it realized that depending on their sensitivity we should design our bandwidth, and therefore you are seeing different bandwidths for different bands, even in case of a 7 bands. But nowadays a different field of remote sensing is being developed, which is hyperspectral. So in case of hyperspectral, the entire spectrum of EM spectrum, a large part of EM spectrum is being covered and in a continuous fashion. That means you don't have segmentations from like one band and another band and so on and so forth. Like here between band 2 and band 3 there is a gap, as you might notice that the highest value is 0.59, the next is 62. That means there is a gap, and this gap is not there in case of hyperspectral. It is continuous. So for each point micrometer there is a band which you are having. So that is why it is very important. Now as I have been mentioning, in a standard false color composite, a infrared channel, as you can see here, is always assigned a red gun or red color, and the green, because these two bands belongs to a visible part of EM spectrum, and green, blue and red, or so the red part is assigned green color, and green is assigned blue color. Now one can argue that what happened to the blue color, because blue color is very close to ultraviolet, and it might have lot of distortions in the image, and since in additive color scheme we can employ only 3 colors. We don't want to give up infrared channel, we don't want to give up the red channel, because ultimately our aim is to differentiate different objects which are present within that image of surface of the earth. So we have in a standard color composite, this is the scheme which is followed, And when somebody writes standard false color composite, automatically that means the green band, which belongs to the visible part of EM spectrum, is assigned blue color. Red band is assigned, which is again visible part of EM spectrum, assigned green color, and infrared is assigned red color. And therefore the vegetation, healthy vegetation, will appear in bright red. And people exploit this thing. If vegetation is not healthy because of some reason, maybe a shortage of water or some disease or forest fire and other things, then this color will change. The reflectivity of vegetation in infrared channel will change, and that can be used to understand all these things. So this is very, very important to understand. Another one is that is simulated true color composite. Here it is tried to create a true color composite image rather than a false color. And in true color composite image, the first one is the same, that the green band assigned blue color, whereas instead of red band, here now we are having infrared band, and which is assigned the green color and the red band. So between red color and green color there is an interchange, and that interchange may bring an image where the vegetation is appearing as green. So for vegetation it is all right, but the rest of the objects which are appearing are not truly in true color, in natural color, and therefore again it's not a complete true color image, but near true color because vegetation is appearing green. So because it is very difficult, if you don't have the continuous or hyperspectral kind of thing, then it is very difficult to create a true color image or natural color image. If you remember somebody is flying from aircraft and looking parts of any part of India, you won't see such images because you don't have the infrared coverage, because our eyes are not sensitive. So most of the time we see gray kind of images, gray or brown kind of part of the land, but even the vegetation may not appear as green as one can see in satellite images, because here the enhancements and other processing is there, plus infrared channel is bringing major changes in your images. This resolution parts we have discussed already, so that basically brings to now end of this presentation, that what is basically image characteristics. The image has to be understood, one, and the unit of the image has to be understood. These are two important things which will help us when we discuss the digital image processing. So thank you very much.